Alrighty, good afternoon, good folks. Let me get a few things moving here, and we can get started. So last week we finished our discussion on volume. I wouldn't mind doing maybe one more cylindrical shells problem if you guys would like. I'll leave that up to you. But then this week we're going to be moving on to chapter 7. This, of course, is MAC2312. Oh, you guys are section 004, right? Yeah, 004. And today is the lecture. It's the 19th. So today you can do more cylindrical shells problems if you want. And then the main thing is we're going to move into chapter 7, which is on integration by parts. Alrighty. So maybe before we get into it, a quick note on the homework. I did get. Oh, damn it! No, Stefan, don't tell me. All right. Rather than doing this, I did get a handful of extension requests from last week, and if you put in an extension request over the weekend or yesterday, I granted it this morning. So all of those should have been granted as of around 8 o'clock this morning. If you do need more time on any of the homeworks, of course, remember you can always just click that little link there that says, request an extension, and I will always grant those. I'll just grant them for 1 week later, and then if you need more time, submit another extension request. That's kind of how it goes. I do 1 week at a time to try and keep you guys on pace with the class. I don't want you falling behind a lot. But if you need more time on any of that stuff, just let me know, and by submitting an extension request, and I will grant them. Let me see, I just see something in the chat here. Why isn't the chat showing up? There it is. Okay, coming up 15. Yeah, sure. So let's look at maybe one more problem from last week's homework, and then we'll move into the new stuff. Please tell me you're going to work. Cengage signing us out like every 15 minutes of inactivity is very frustrating. So Josh wanted to see number 15, was it? Yeah. So here we want to use the method of cylindrical shells to find the volume of the solid obtained by rotating the region bounded by the curves y equals x to 3/2, y equals 8, x equals 0, about the x-axis. All right, let's do it. I'll copy this down. This is homework 2, number 15. Find the volume blah blah blah, y equals x to the 3/2, y equals 8, x equals 0, about the x-axis. And we want to use shells. Okay. So here's the setup. Now let's see. I need to know first what this curve y equals x to 3/2 looks like. And he's not super duper obvious, so I'm going to spend a second talking about how to get that curve. Y equals 8, this is a horizontal line, and x equals 0, that's the y-axis. And we want to rotate everything about the x-axis. Since we're using the shells method and rotating about a horizontal axis, everything is going to need to be done in terms of the variable y. Okay. X equals 0, that's the y-axis. The x-axis is my axis of rotation. y equals x to the 3 halves. This is the cube root of x, I'm sorry, the cube of x under a square root, or the square root of x cubed. This power is bigger than 1, which tells me a little bit about the shape. It tells me that the shape is going to be kind of convex, like, or concave like this, rather than being convex like this. Let me show you some things in Desmos real quick. This can be helpful. Just to... If you don't have these graph shapes memorized, x to the 1/2, that's the square root function, right? And it has this kind of convex shape, it's puffy. X to the 3 halves, the power is bigger than 1, it'll have this kind of concave shape, like x squared or x cubed. Right? So if you look in the first quadrant, x cubed, all of the power functions where the power is bigger than 1 have this same sort of shape in the first quadrant. So our guy, x to the 3 halves, is going to have that same shape because the power is bigger than 1. It's going to have this concave shape rather than that convex shape. So my curve here, something like this. Certainly 0 to the 3 halves is 0. And then I've got the horizontal line y equals 8. I'll draw that in like this. I want to rotate about this axis, right? So my region here, like this, and I want to rotate about this axis, which is a horizontal axis. So using the method of cylindrical shells, is my strip going to go in like this or like this? Do I orient my strip horizontally or vertically? That's the rule.
Horizontal.
Good. It'll be horizontal because it needs to be parallel to the axis of rotation, right? That's what makes this method this method. So draw in my strip. Its thickness is a little dy thickness. So my integral is going to be a dy integral, which means I need to characterize the point on the curve here in terms of y. Meaning I think of y as being the independent variable, and I have to figure out what x is as a function of y. Since this curve is y equals x to the 3 halves, that's the same as saying, let's square both sides. Y squared is equal to x cubed. And then take the cube root on both sides. Y to the 2/3 is the same as x. So everywhere along this curve, you can think of it as being x comma x to the 3 halves, because y is x to the 3 halves, or you can think of it as y to the 2/3 comma y. And that's how we're going to think of it. Because I need everything here to be in terms of y, because this thickness is a dy thickness, which means my integral will be a dy integral. Now, if I rotate just that strip about the axis of rotation here, I'll generate a little cylindrical shell. Looking something like this. All right, looking something like this. So, my axis of rotation. Looks like this. And I need to think of a few things. I need the dimension that we've been calling the radius, which is this. Right, this distance here from the axis of rotation out to the edge of that thing. And I need this dimension that we've been calling the height of the cylindrical shell. Because then I know that the volume of that little shell is 2 pi r h, in this case, times dy. That little wall thickness here is dy. So r in this picture is what? Just in terms of distances, what is r?
Y.
So again, in terms of distances, how would you describe what that radius is in just regular English language?
8 minus y.
The distance from the x-axis to the point.
Good, yeah, it's the distance from the axis of rotation to the strip. So that's going to be this distance right here, yeah? The distance from the axis of rotation up to this strip. And you're correct in saying that it's y, right? Because the y value up here is y, and the y value down here is 0. And then the other dimension that I need is h, which is like the length or height of my strip. And in this case, h is y to the 2/3, because I would take the x value here minus the x value here. The x value over here is y to the 2/3. The x value over here is 0. So dv is 2 pi y times y to the 2/3 dy. Everybody comfy with where these things are coming from?
I was really uncomfortable with this problem, and I did it like a weird way, but in the end I got a correct answer. Instead of rewording the equation to form in terms of y and x, I recognized that you could make a rectangle with this little section that you cut out here, find it just using the original equation, and then minus it from the area of the rectangle to get the other area. And then you could rotate that around the x-axis.
It sounds like what you're doing there is maybe more similar to using a, so you're thinking about this big rectangle,
Yeah.
rotating that rectangle, and then subtracting out this region. I see. Yeah, that's a hack. It'll work. But we really need to get comfortable with this idea of horizontal and vertical axes of rotation for both the shells and disc washer method.
Yeah,
so use it as an archetype, right? So spend some time trying to get comfy with these.
Yeah, it was just a very uncomfy problem.
Are you feeling comfier? Are we getting closer to being okay with this setup?
Yeah, I think so.
Okay. So a little bit of practice, and we can avoid those sort of hacks, and that'll help things make more sense in context. So then v is going to be the integral of dv, and I'm going to integrate from whatever the smallest y value is in my region, right, to whatever the largest y value is in my region. So down here y is 0, and up here y is 8. So we're going to integrate from y equals 0 up to y equals 8. And then I'll just plug in for dv. I'll continue this over here. It'll be the integral from 0 to 8 of 2 pi y times y to the 2/3 dy, and out can come the 2 pi, integral 0 to 8. Y to the 1 is y to the 3/3. 3/3 plus 2/3 is 5/3. So this is y to the 5/3 dy. And now I'm ready to integrate. So I've got this written as a power function. So that'll be 2 pi times 5/3 plus 1 is 8/3. And if I divide by 8/3, that's the same as multiplying by 3/8. So I'll have 3/8 y to the 8/3 evaluated from 0 to 8. If we go ahead and do that evaluation, of course, when we plug in 0, we're not going to get anything. But when we plug in 8, I'll have 2 pi times 3/8 times 8 to the 8/3. Now the 2 and the 8 here can talk to each other. That'll give me 3 pi over 4 times 8 to the 8/3. And then you can handle this power. This is the cube root of 8 all to the 8. The cube root of 8 is 2, so that's 2 to the 8. Uh, 4 is 2 squared, so you can kind of get sloppy at this point. This is 3 pi. 2 to the 8 divided by 2 squared is 2 to the 6, which is 64. And it's up to you if you want to clean this all the way up. 3 times 60 is 180, plus 3 times 4 is 12, so it's 192 pi. But I would be happy once you get to here. Just in case you need it, here are the last few steps.
On a test, do you want us to write out the -0, or like the minus? Do you want us to plug in?
It's up to you. You know, you could if you wanted to. If you omit it, that's okay as well. Just make sure you don't omit it if it does contribute something, right? If this was a 1, or if this function wasn't 0 when you plug in 0, then I would want you to write whatever comes from that. But if you know that nothing comes from this lower limit, you can skip writing it. Just make sure that you're correct in that.
I have a question about the very beginning.
Yeah.
When you said we need everything in terms of y, how do you determine that?
Because the strip's orientation is like horizontal. So that makes its thickness a dy thickness. As soon as I drew this, I knew that everything was going to have to be done in terms of y.
And is that the same with this washer?
It is. Yep. If the strip is horizontal, then its thickness will be a dy thickness. And regardless of the method you're using, that means everything needs to be done in terms of the variable y. Yeah, that's the giveaway there.
Okay, thank you.
Of course. Any other questions on this one? Comments, concerns?
So are you imagining like the blue square like going up and down between 0 and 8?
Yeah. So I imagine like that strip could be down here. And I imagine that that strip could be all the way up here. And for each of those locations, I get a different kind of cylindrical shell. So I need the formula for the volume of this shell as a function of the y value where the strip is located. Does that make sense?
Yeah, that makes sense.
So again, it might be useful to sort of come back here and take a look at these now that we've had some time with them. This is the visualization for cylindrical shells. To kind of try and see how this can generate the whole solid.
The problem to be different technique here. If we start revolving it, notice
So there's one strip giving one shell.
Here we're
But then if you had a shitload of strips, they'd give you a shitload of shells that look a lot like the whole solid. So you have to imagine there being a strip at every possible y value, or in this case, every possible x value.
here.
And then you go through a computation. You know. But that visualization, that's, I think, very useful. So look, all these different strips. If you wanted to get the whole solid, you would have to have an infinitely thin strip at every single x value along this region. So you have to imagine what's the volume when the strip is here? What's the volume when the strip is here? You come up with a formula for that. And then imagining stacking the results from all those strips. That's what the integral does.
Stack up to form.
Does that help a little bit? Okay. I do want to get into the new material. The new thing that we're talking about this week is kind of a big deal, and it's not a super easy thing to wrap your head around. So if you want to talk about more cylindrical shells or volume problems in general with me, come by an office hour. I had an office hour today from 11 to 12. I have another one tomorrow from 1 to 2. And that is really a perfect place to talk about extra problems. And I would be happy to do that with you guys if you like. But we need to move on with a new kind of, really it's a big jump for us. We're no longer going to talk about applications here. We're beginning chapter 7. Which is all about techniques for integration. And this is really the first big part of this class. So, you know, chapter 6 is a little warm up. This is where Calc 2 really begins in earnest. You know your basic antiderivative formulas, and you know how to do U substitution. Those are good. Those are a good start. But it turns out that that's not nearly enough to even begin scratching the surface of all the things we can or want to integrate. So in each section of chapter 7, I'm going to teach you a new technique for integration. And each one of these is about as difficult to learn as U sub was. The difference is you're not going to have, you know, 6 weeks between when you first hear these and when you're tested on them, like it is for U sub, where you just heard about it at the end of Calc 1 and you're really going to have to be put to the test on it. In Calc 2 here, you're going to have to master these pretty quickly, which means you're going to need to dump a lot of time in. The first method we're going to learn is called integration by parts. And you'll see me abbreviate this a lot as IBP. It's a backwards product rule. And I mean that very literally in the sense that the way you prove this is by taking the product rule and integrating. So let's look at the product rule. The product rule says if I have two functions, u and v, and they're multiplying each other, and I want to prime them, so take their derivative, the way that's done is you differentiate the first and you leave the second alone. And then you add that to what you get when you leave the first alone and differentiate the second. Now, if I integrate on both sides, this, by the way, is where I said, you know, remember I said we're going to use the variable u to mean something specific. This is that place. So now if I integrate on both sides, what do we get? I get the integral of u times v all primed equals the integral of u prime times v plus u times v primed. Now the implicit thing here is that the variable is x, right? So this is kind of informal. So really what I'm saying is that the integral of d dx u times v dx is equal to the integral of d dx of u times v dx plus the integral of u times d dx of v dx. Now, if you cancel out all the bits, over here, the dx's cancel and the integral cancels with this derivative, and you just get u times v. Over here, the dx's are going to cancel, and you're going to get the integral of v times du. And over here, you're going to get the dx's cancel, the integral of u times dv. This is the IBP formula. But most people rearrange it to say that the integral of u dv is equal to u times v minus the integral of v du. All right, so specifically this piece is the piece that most people memorize. But it really does follow from the product rule. You just take the product rule and integrate on both sides. Here, implicitly, we understand that u is a function of x and v is a function of x. So du and dv are differentials calculated in terms of the variable x. That's the idea. Sorry, I haven't had time to really eat anything today. All right. So make sure this formula gets into your notes somewhere nice and clean. There's a version for definite integrals. It says that the integral from a to b of u dv is equal to u times v evaluated from a to b minus the integral from a to b of v times du. People forget to evaluate this part all the time. Don't be that guy. Or girl. Don't be that person. So there's your IBP formula for definite integrals. Let me show you how to use this. Everybody got the formulas down?
Just a second more.
Sure. Okay. So, you know how to integrate x, and you know how to integrate e to the x. But how would you integrate x times e to the x? Quick note, this is not x squared over 2 times e to the x plus c. This shit don't work. The integral of f of x times g of x is definitely not the integral of f of x times the integral of g of x. Right, just like the product rule. When you want to differentiate a product of two functions, you can't just differentiate the two and multiply them. It doesn't work. We have a product rule. If you wanted to differentiate x times e to the x, you would need to use the product rule. So here you're going to need to use the backwards product rule. The backwards product rule is called integration by parts. So here's the way this is done. You have to partition your integrand into two pieces. You have to pick a piece to call u, and you have to pick a piece to call dv. I am going to pick u to be x and dv to be e to the x dx. Because I need my original integral to be the integral of u times dv, right? That's what we have in our formula. So what we do to run IBP, this is called forming a partition or partitioning into u and dv such that u times dv is the whole thing. All right, so my integrand is x e to the x dx. So if I pick u to be x and dv to be e to the x dx, then u times dv is x times e to the x dx. That is this thing. In other words, you split up your integrand. You call part of it u, and you call the rest of it dv. Now, from u, you calculate du. That's the differential, right? So just like when you're doing a u sub, if u is x, then du would be dx. And from dv, you calculate v. Now to go from a differential back to v, you need to integrate. So the integral of e to the x dx is just e to the x. So after you do that, then you calculate du from u by differentiating. And you calculate v from dv by integrating. So every time you want to use IBP, you're going to make a little table like this. You start by partitioning your integrand into u and dv. And you choose part of your integrand to be u, part of your integrand to be dv. And you make sure that when you multiply this shit by this shit, you get the whole thing up here exactly as it was in the original. Once you've chosen how to split your thing up into u and dv, you differentiate u to find du, and you integrate dv to find v. Now you apply the formula. It says that the integral of u times dv is equal to u times v minus the integral of v times du. Let's see what that says for our choices of u and v. That would say that the integral of u times dv, x times e to the x dx, is equal to u times v, that's x times e to the x, minus the integral of v times du, e to the x dx. Notice that the thing on the left is the thing I want, and that the thing on the right contains a piece here to which I need do nothing, and an integral here, which is easier than the integral I started with. That's the magic of IBP. Now we just evaluate this integral. So this is x e to the x minus an antiderivative for e to the x. That's just e to the x. Slap on your plus c and you're done, baby. That is the antiderivative for x e to the x. Not too bad, right? It's really just a backwards product rule. It's a product rule for integrals, but it takes a little getting used to because the notation is kind of weird.
So would it have mattered if we chose different u versus dv? Like if we had switched it around, Would
Yeah,
it have changed the outcome?
it would have. Yeah, that's a good question.
Well, in that case, how do we guess the correct parts of the function?
I'm going to show you a few tools for that.
Okay,
Um,
interesting.
so when I learned this, I was told, you know, you gotta figure it out. You just gotta play with it and see. So if after you write down your IBP formula and plug shit in, if the integral over here is not nicer than the integral you started with, then you should go back and try something else. But there's a much better way. There's a much better rule here. There's a rule for choosing U and dV. L stands for log. I stands for inverse. P stands for polynomial. E stands for exponential. T stands for trig. Think of this as a hierarchy. If you have any logs in your integral, you should choose that to be U and everything else to be dV. So if any logs, choose that as U and everything else as dV. That's what this first row is saying. The second row here, if there are no logs, but there are inverse functions, choose those as U and everything else as dV. Now, if there are no logs and no inverse functions, you get where this is going, right? But there are polynomials, choose those as U and everything else.
So wait, by this logic, shouldn't we have made e to the x our u since it's an exponential?
Well, which one of these do you hit first as you go down the list? Polynomial, right?
Well, does x qualify as a polynomial? Because that only
Absolutely.
seems like one term.
No, yeah, X is definitely a polynomial. Polynomial is any combination of constants times integer powers of X, or, you know, positive integer powers of X. X itself is definitely a polynomial.
I thought a polynomial had to be like a binomial or more.
Nope, monomials are all polynomials.
Okay.
Yeah. As long as the powers of X are non-negative integers, then you're looking at a polynomial. So we look at my integral. Are there any logs? Nope. Okay. Are there any inverse functions? Nope. Okay. Are there any polynomials? Yes. Okay. So I choose the polynomial to be U and everything else to be dV. And that's what we did, right? That's what we chose here. Chose X to be U, which is the polynomial portion, and everything else, e to the x dx, to be dV. This LIPET rule works really well. Works about 95% of the time. There are some problems on which this does not work, and in those you're just going to have to fiddle around, right? And I'll show you a few examples of problems like that, and kind of how I work my way through them, but we'll build up to that.
Professor?
Yeah.
I have a question.
Sure.
What about the rare case where your integration of parts turns into itself?
We'll get there. Yeah, looping integrals are day 2 of IBP. So today we're day 1 of IBP. Day 2 of IBP, I will show you some looping integrals. Things like e to the x cos x, secant cubed of x, odd powers of secant in general are things like that. where you run IBP a few times and then your original integral shows back up. I call those looping integrals, and I'll show you how to handle those next time.
Thank you.
I have
But
a
for now, we're gonna get a little bit of practice with this, and I'm gonna show you guys how to integrate some kind of basic functions that up until now we weren't able to. Does everybody have the LIPET rule in their notes and this example nice and clear in their notes? Would anybody like more time to write things down? If not, I am going to move on. Okay. So, we just did the integral of x e to the x. X squared times sine x is similar. If I follow my LIPET rule, I don't have any logs, I don't have any inverses, but I do have a polynomial, right? The x squared piece is a polynomial. So I'm going to pick u to be my polynomial piece and dv to be everything else. I like to label my table here as an IBP table so people can tell what's going on. I calculate du, which is 2x dx, and I calculate v, antiderivative of sine is negative cos x. And then following my integration by parts formula, the integral of, this is u times dv. The integral of u times dv is always u times v minus the integral of v times du. So that's x squared times negative cos x minus the integral of v, which is negative cos x, times du, which is 2x dx. And there's some cleaning up that can be done here. This is negative x squared cos x plus 2 integral x cos x dx. And now when I look at the integral I have here, integral of x cos x dx, it's kind of similar to the integral I started with. It's a polynomial piece times a trig piece. And if I was going to differentiate x times cos x, I would use the product rule. So if I want to integrate it, I should use IBP. So we're going to do another run of IBP. This time I will again choose u to be my polynomial and dv to be everything else, which is cos x dx. Du is just dx then, and v will be the integral of cos x is sine x. So here's my second little IBP table. And I just need to be careful. This piece out front comes along for the ride. Negative x squared cos x, he's just chilling. And then I've got my plus 2 times. And now this integral, I'm about to replace him by a difference of 2 terms coming from his own integration by parts. So I need to make sure this 2 gets to everything in here. So I open up a big parentheses. And then I'll have u times v, which is x times sine x, minus the integral of v times du, which is sine x dx.
Professor, I have a question.
Sure.
Why do we do the IBP again?
Well, so once I get to this line right here, to finish the problem, I need to solve this integral. And this integral is itself a polynomial times a trig function. So the hint to use integration by parts on this piece is that if you wanted to differentiate this, you would need the product rule, right? It is a product, x times cos x. That's one function times another. So for the same reason I used IBP at the start, because I had a product of two functions, I'm going to use IBP down here. This actually looks a lot like that. The sine became a cosine and the x squared became an x, but I still have the same sort of pieces. I still have a polynomial function times a trig function. So anytime you encounter something like that, polynomial times sine, polynomial times cosine, those are all IBP problems.
Got it. Thank you.
Of course. Another kind of way to think about this is that you know, what else could we possibly do here, right? There's no useful u substitution. These things are multiplying, they're not adding up, so I can't like split up the integral. So none of the other tools we know so far work, so we might as well try IBP. But really the thing is it's a product. It's one function times another function, and that means I should try integration by parts.
So why couldn't we use the product rule with the original integration?
We did. IBP is the product rule for integrals, right? We're not differentiating, we're integrating. So the product rule is for differentiating. IBP is the integral version of the product rule. And it's precisely the same reason we used it here that we use it here. Because if I wanted to differentiate this, I would use the product rule. That tells me that if I want to integrate it, I should use IBP. And then the same logic down here. If I wanted to differentiate this, I would use the product rule. But I don't want to differentiate it, I want to integrate it. So I should use the integral version of the product rule, which is IBP. So let's finish this up, and then I'll give another sort of general guideline hints as to what to use when. Negative x squared cos x, still chilling. I'm going to distribute this 2 now, so I'll have plus 2x sine x minus 2 times the integral of sine x dx. And then the integral of sine x we can calculate. So I get negative x squared cos x plus 2x sine x. Who differentiates to sine? That's negative cosine. So the negative there and the negative here will eat each other up, and we'll get plus 2 cos x plus c. So that's the result there. And then another sort of general guideline, like the LIPET thing, is anytime we want to integrate something like polynomial times trig, or integrate something like polynomial times exponential, these will be IBP. These will require IBP, and the number of IBP runs needed is equal to the degree of the polynomial. So like in this problem, I had a degree 2 polynomial, x squared times sine x, and I needed 2 runs of IBP. If I wanted to integrate x cubed minus 5x plus 7 times e to the x, I would have to run integration by parts 3 times, because the degree of that polynomial is 3. So anytime you want to integrate polynomial times trig, or polynomial times exponential, you're going to use integration by parts, and the number of times you're going to need to use the IBP formula is always the degree of the polynomial.
I had a couple of questions.
Sure, Alexander, go ahead.
Thank you. Wouldn't there also be cases where you'd have like poly times trig and you could use U sub?
Sure, yeah, I guess I should be a little bit more clear. If this is just sine x or cos x, I should say here. And you have a more complicated polynomial here, those are the instances where you will need integration by parts. If the polynomial outside here was exactly the derivative of the inside of the trig function there, then you can get away with a straight U sub.
Okay.
Certainly in the case we have a higher order polynomial times sine x or cos x, then you will need IBP.
And then my second question was, what if there's more than 2 factors in the original integral?
That depends. Then you can split that integral up, right? If you've got like, you know, a chunk of shit over here plus a chunk of shit over here, and each one of those kind of look like IBP problems, you can split up the integral and attack each one separately, or you can look for a way to combine them. Maybe you can factor something out and treat it as a single approach. Like if you had x squared e to the x minus 2x e to the x, then you could factor in e to the x out and treat that as x squared minus 2 times e to the x. And that way you could get away with a single integral and kind of one path, but it would still require 2 runs of integration by parts. So really the answers are, there's so many paths in Calc 2 that will lead you to the right solution, especially when it comes to integrals, that you really need to play around with them and sort of develop a style of your own. What I'm showing you here is just the absolute barest of framework that can get you started, and then you need to use this as a skeleton on which you can lay the flesh of your own integration style. But there's more to this skeleton. So before we get into any sort of stylistic choices, there are a few other really basic things I need to show you with integration by parts. How are we doing?
I have a quick question. How come x squared is considered a polynomial and not an exponential in this?
Well, remember definition of polynomial. So polynomials are anything of the form some number times x to the n plus some other number times x to the n minus 1 plus all the way down to a1x plus a0. So here the powers are positive whole number constants. An exponential, these are functions like b to the x, where b is a constant. So if the variable is in the power, then that's an exponential. If the variable is in the base and the power is a positive constant, then that's a polynomial. So things like x squared or 2x cubed plus 7x minus 3, or even x on its own, or 5x to the 7, these are all polynomials. Things like e to the x, 2 to the negative x, or 3 to the x, these are exponentials. Right, so polynomial power is in the base. Polynomial variable is in the base, and the powers are positive whole numbers.
Got it. Thank you.
Exponential power is the variable. The variable is in the power. All right. Other kind of basic stuff we need to know how to do with IBP is how to integrate inverse functions. We know how to integrate e to the x. What about the natural log? We're real proud of our integration skills until we start like running down the list of fundamental functions and realizing how many of them we don't know how to integrate. Natural log is definitely one of our fundamental functions. We know that his derivative is 1 over x, but what is his integral? Give me just 1 second. baby, is the stove on? I've been smelling something burning. Can you take a look and see if the stove is on? All right. So can we integrate the natural log function? It's a big
Yes.
question. Yeah. Thank goodness. Yes, we can. The trick here is going to be to use integration by parts, and it's not a super obvious path. But if you follow the LIPET rule, it will kind of take care of things for you. So remember, this is a hierarchy for choosing u. And since right away we do have an L, we do have a logarithm. So I'll pick u to be the logarithm, which is the natural log of x, and dv to be everything else. Well, everything else here is just dx. Then according to my IBP formula, the integral of u times dv, which is the integral of ln x times dx, should be equal to u times v minus the integral of v times du. So I calculate du from u, that's 1 over x dx, and I calculate v from dv. So if u is ln x, then du is 1 over x dx. If dv is dx, then v is equal to x. So u times v is the natural log of x times x minus the integral of v times du is the integral of x times 1 over x dx. And now we can simplify the integral on the right. I'll also rewrite this as x times ln x. Just putting the power function out front. It's just kind of the standard notation. And then within my integral here, x times 1 over x, that's just 1. The x's cancel. And the integral of 1 dx is x. So this is x ln x minus x plus a constant. And that's how you integrate the natural log. And more generally, that's how you integrate any logarithm function. You run IBP with u equal to the logarithm piece and dv equal to everything else, whatever that everything else might be.
I'm sorry, I kind of got lost. Can you go over this again really quick?
So we want to integrate the natural log of x dx. Following our LIPET rule, which tells us how to pick u, we run right away into an L, into a logarithm. So I'm going to choose u to be the logarithm. And then dv is always everything else, whatever else is left. Well, dv, the only thing that's left is the dx. So dv is going to be dx. So now u times dv, that is my whole integral. So I calculate du from u. The derivative of ln x is 1 over x. So du is 1 over x dx. And I calculate v from dv. Since dv is equal to dx, if you integrate on both sides, you get v equals x. Now my integration by parts formula says the integral of u times dv is equal to u times v minus the integral of v times du. So I'm just going to plug into this formula. U is the natural log of x, and v is x. So u times v is ln x times x minus the integral of v times du. Well, v is x, and du is 1 over x dx. So v here is x, and du is 1 over x times dx. So my IBP formula gets us here. Now we're on our own. From here, we got to figure out what to do. But this integral is easy. The x's cancel, right? X times 1 over x, just like 2 times 1/2 or 3 times 1/3, those are all 1. X times 1 over x is 1. So this is the integral of 1, which is just x. So we get x ln x minus the integral of 1 dx, which is x ln x minus x. And then I slap on my plus c here because I'm done with all the integrals.
In our IBP chart, we basically differentiate the left side and then integrate the right side.
Correct. Yeah, to get du from u, you need to differentiate. To get v from dv, you need to integrate. All right, how am I doing on time here? 1:30. We got about 15 minutes. I have one more important example that I want to show you. So let's get to that. Which one do I want to do? I'll do the inverse sine function. All right, and this is going to be the last indefinite integral I do. After this, I'll do one example with a definite integral. Again, this isn't something we know how to do. This isn't something that we can handle with a u sub. It's not something we can handle just using basic antiderivative rules. So we can kind of lecture logic our way to this should be done using by parts. It's a new problem, and by parts is our new method. Again, following LIPET. I don't have any logs, but I do have an inverse function. So I'm going to run integration by parts with u equal to my inverse function, which is sine inverse x, and dv equal to everything else, which in this case is just dx. Now I calculate du and I calculate v. I'll do v. You tell me, what is du? What is the derivative of the inverse sine function?
If I remember correctly, it's 1 over the square root of 1 minus x squared.
Perfect.
Oh, did I actually get that right? Cool.
That's it. Yeah. That's perfect. So now we are ready. We're going to take our IBP table and plug into our IBP formula. It says the integral of this thing, which is u times dv, should be equal to u times v, which is sine inverse of x times x, minus the integral of v times du, which is x times 1 over the square root of 1 minus x squared dx. Yeah, that's perfect. So this is as far as my integration by parts formula will take me. The piece out front here is done. I don't have to do anything with that. How do we do this integral?
Can you u sub the piece inside the square root?
Very good. Yeah, that's the game. We're going to do this with a u sub. Now I'm going to use the letter z here because I don't want to confuse it with what's going on back there with the u. So I'm going to sub z equals 1 minus x squared. dz then is negative 2x dx, which means negative 1/2 dz is equal to x dx. So I've got an x dx. I'll rewrite this maybe just for a second. 1 over the square root of 1 minus x squared times x dx. So you can see what I'm doing. This piece right here, I'm going to replace by negative 1/2 dz. And this piece right here is going to be 1 over the square root of z. All right, so that's how this U sub shakes out. Hopefully you guys are feeling comfy with U sub after last week. Oh, and I left off my x here. I've got x times sine inverse x. So this is x times sine inverse of x minus integral 1 over the square root of z times negative 1/2 dz. I can pop the negative 1/2 out front. I get x sine inverse of x plus 1/2 integral 1 over the square root of z is integral of z to the negative 1/2 dz. And now to do this integral, I have to add 1 to the power, divide by the new power. So that's x sine inverse of x plus 1/2 z to the negative 1/2 plus 1 is z to the positive 1/2. And when you divide by 1/2, that's the same as multiplying by 2. Slap on your plus c. And now finally go back to the original variable. So you get x sine inverse of x. The 2's and the 1/2's cancel, plus parentheses 1 minus x squared to the 1/2 power plus c. And that's it. Oh. Question, can this power cancel with this x squared here? Is this just 1 minus x?
No, it's different to squares.
The inside is a difference of squares, yeah.
Right.
But I can't distribute powers over addition or subtraction ever, right? So even if we factor the inside as a difference of squares, I still wouldn't be able to make that go. All right. That's the antiderivative for the inverse sine function. You can write it in terms of a square root like this, x sine inverse x plus the square root of 1 minus x squared. And you'll see it written like this a lot. And this process is very similar for the inverse sine function, inverse cosine function, and inverse tangent function. All of the inverse trig functions run the same way. You do IBP once, and then a little U sum. So if I asked you to integrate inverse tangent, inverse cosine, they would be done precisely the same. To get started on all of those, you need to know the derivative of the inverse trig functions. So I would add to your notes here, I'll put it over here. Sine inverse of x primed, that's the one we used here. That's 1 over the square root of 1 minus x squared. Cos inverse of x primed is the negative of this, negative 1 over the square root of 1 minus x squared. Tan inverse of x primed is 1 over 1 plus x squared, no square root. Maybe I'll just leave it at these for now. The secant, cosecant, and cotangent derivatives, inverse derivatives, are not as often encountered, but these three, at the very least, you need to know. Gotta know these. I'd let you off the hook for not knowing the derivative of the inverse secant function, but if you don't know the derivative of the inverse tangent function, I can't help you. You gotta know that shit.
So to clarify, we don't need to know the inverse of secant, cotan, or cosecant.
I would not necessarily expect you to have memorized the derivatives of the inverse secant, cosecant, or cotangent functions, yeah. So on a test, for example, I wouldn't give you a problem that required you to know those on the fly. I could put them in the homework, but I wouldn't put them on a test. On the test, I could give you a problem that requires you to know these on the fly. Fair enough?
Yeah.
All right. Okay, how are we doing on time? We got time for a definite integral? We're gonna have to wait on those. It's 1:39, we got 6 minutes left. So I'm gonna go ahead and show you one definite integral done by parts. Not too bad, it's really not. You just have to make sure you remember to evaluate all the pieces. Shit, let's do, what haven't we done yet? let's integrate x e to the negative x from 0 to 1. Well, so this is going to be done by parts, just like x e to the x was. Here I'll choose u to be my polynomial piece and dv to be my everything else, which is e to the negative x dx. Du is just dx. What is v? What is an antiderivative for e to the negative x? This is actually a tiny little u sub problem buried inside my IBP. You notice that? If I asked you to integrate e to the negative x on its own, most people would make a little u sub. U equals negative x, du is negative dx, blah, blah, blah. This is going to come out to negative e to the negative x. And you want to get to a place where you can do those micro u subs very quickly. So small note, integral e to the ax dx is always 1 over a e to the ax. Similar for sine and cosine. Sine ax dx, this is always 1 over a sine a, 1 over a negative 1 over a cos ax, and integral cos ax dx is always 1 over a sine ax. I'm leaving off the plus c's. Just basic antiderivative stuff, micro u subs that you need to be able to do quickly. So here, u is x, so du is dx. dv is e to the negative x. So v is e to the negative x over negative 1, which I'm writing as just negative e to the negative x. Which means my IBP formula is going to be u times v, which is x times negative e to the negative x, all evaluated between bounds, minus the integral between bounds of v times du, which is negative e to the negative x dx. Now we can evaluate this first piece. At 0, I get nothing. I'll have 0 times 1, or 0 times negative 1. But at 1, I'll get 1 times negative e to the negative 1. Minus. Actually, the minus here is going to make a plus. And then I'll have integral 0 to 1 e to the negative x dx. Just pulling that negative from my integral here out. You always want to evaluate this piece right away. Some people like to wait till the very end of the problem to do this evaluation. Don't do that, because you're going to end up writing a whole bunch of shit when you could just write negative e to the negative 1. And now my antiderivative over here is negative e to the negative x again. And he'll get evaluated from 0 to 1. So this is negative e to the negative 1 plus, at 1, I get negative e to the negative 1. And then you have to subtract off what you get at 0 minus negative b to the negative 0. So this is negative e to the negative 1 minus e to the negative 1 plus e to the 0, which is 1. And this piece right here is negative 1. So minus negative 1 makes plus 1. In other words, here we have 1 minus 2 over e. This is negative 1 over e minus 1 over e. That's negative 2 over e. And this is the 1. So this is a definite integral. Next time, I'm going to show you more definite integrals by parts. And I'll also show you looping integrals, which were the thing that I think it was Cody or Alexander asked about at the start of class today, where the original integrand actually loops around and shows back up after some amount of massaging and integration by parts. For now, though, I want you guys to focus. I'm about to open up a fresh homework assignment. I want you to focus just on like the first 5 or 6 problems for this week, at least today. That way you can get a little bit more comfy. Make sure you solve at least 5 or 6 of them today. And then you'll be in good shape to move forwards from here. I don't want you to go long enough to forget, but I also don't want you to charge too deep in the homework set and be overwhelmed, because there will be some harder problems in there, and you deserve to ramp up slowly. Any questions before we sign up for the day?
I don't know if you said it before, Professor. I didn't hear it before, but are there office hours today at 4?
Office hours today were 11 to 12. I will
Okay.
have more office hours tomorrow from 1 to 2.
Okay.
But yeah, that's it for today.
I will go to those then. Thank you.
All right, cool. Any other questions before we scoot?
No,
Where do we
have a
find
good
the
day,
Zoom
Professor?
link?
Oh, I'm sorry. I think I heard 2 things. Alexander, what were you saying?
Where do we find the Zoom link for tomorrow's office hours? Is it still on the Canvas page?
Yeah, so those links, those don't change. So they will always be right here. So the Monday, Wednesday, Friday office hour, that's 1 to 2, and you can always click this link to join it. And the Tuesday, Thursday office hour from 11 to 12, you can always click this link to join. Cool, and so it's on the home page or the syllabus page in our Canvas course.
Thank you.
And then what was the other question? I think somebody else was saying something just as he did.
I think someone else is saying just have a good day.
Okay. If there aren't any other questions, then I am going to go ahead and sign out for the day. Last call for questions before we go. All right, guys, I wish you all the best. If you do get stuck on anything, don't hesitate to reach out for help. You can come to my office hour tomorrow, or if you want a faster reply, just take a little picture of your work, whatever it is you're working on, email it to me, or send in a Canvas message, and I'll give you a little hint or a nudge in the right direction. Watch for the new homework to drop. It'll be open in the next few minutes, and that is it. I'll see you guys on Thursday.